Okay, well, let's start with this example, right? So we have a bivariate table, and it's a table basically wanting to know the significance of handgun sales to homicide rates. So basically, the question is, as handgun sales, do they have an effect on homicide rates, right? So it's a bivariate table. Um, Therefore, we can use chi-square, right? But before we can do that, we have to find the F expected, right? And the F expected is simply this formula here, right? F expected is equal to row marginal times column marginal divided by n, right? So the thing that we have to do is we have to find the row marginal for each one. I mean the F expected for each one of these, right? So for 12, for 8, it is simply 12 times 13 divided by 25. So if we put it up here, 12 times 13 divided by 25, and that would give us 6.24, right? For 4, it is 12 times 12 divided by 25, right? 12 times 12 divided by 25, and it gives us 6.76, right? For the next one, 5, it is 13 times 13 divided by 25, right? And that'll give us 6.76, right? That's a 6, by the way. And for the next one, it's row 12 times column 13 divided by 25 n, right? So that is 13 times 12 divided by 25, and that'll give us 6.24, right? So that is the best way. I mean, that is the way that we get F expected for each one of these, right? So we got our F expected, but is this the easiest way to do this? No. The best way to do this is to set it up as a table. So we have our list of F expected, right? So the next thing we're going to do is we're going to put this into a table. It'll help us out. Okay, so this is a table that's set up from the PowerPoints too. So we're just going to go along. Okay, so we found our F expected, and we found our F expected. We listed them as F of E, right? So let's just call this 1, right? So that was the first thing we did. Our F observed is always just what we were given. So we were given these in the table, 8, 5, 4, and 8, right? That's our F observed, right? So in the formula for the first thing that we have to, the second thing we have to do is we have to subtract, and this is the first thing right here, right? This part in here, we have to subtract our F observed from our F expected, right? So what we would do is we simply are going to subtract 6.24 from our F observed, which is 8. So if we had a little red mark here, we'll just subtract, right? So if we were to subtract these, 8 minus 6.24 is 1.76. 5 minus 6.76 is negative 1.76, right? 4 minus 5.76 is also negative 1.76, and 8 minus 6.24 is 1.76, right? So the next part, it says, the next part of our, so this is step 1 here. Now step 2 means that we have to square it. So we're still going with what's inside of the formula. It just simply said that F observed minus F expected, we need to square. So we've already subtracted our F observed from minus our F expected. So all we got to do is square these. So 1.76 squared is 3.10, right? So 1.76 times 1.76 equals 3.1, right? So same thing, if we square a negative, it comes out to be a positive, right? 3.1 and 3.1, right? So we've done So let's call this step number 2, step number 3, and now we're at step number 4. And step number 4 says, hey, we need to divide this by f expected. So for each one of these, we're going to divide it by its individual f expected. So what we would divide it by is, for this, we're going to divide it by this f expected. For this one, we're going to divide it by this f expected, right? And so on, right? So 3.10 divided by 6.24 is going to give us 0.5. 3.10 divided by 6.76 is going to give us 0.46. 3.10 or 3.1 divided by 5.76 is going to give us 0.54, right? And 3.1 divided by 3.1 divided by 6.24 is going to give us 0.50. Okay, so we see this uppercase sigma. It means to add everything up, right? So that's the final thing we have to do, right? Our final step is that we add all of these up, and we add them up, we get 2.0. So in essence, our chi-square is 2.0. So we've discovered that our chi-square is 2.0, right? And that's how we determine chi-square. But we're not done with this, because our hypothesis was that f observed equaled f expected, right? And our alternative was that f observed did not equal f expected, right? So we have an additional step, and our additional step here is that we need to come up with a critical area, right? So we found that our our chi-square is 2.0, right? We're not done, because we haven't determined if this is in a critical area and we can reject or accept our hypothesis, right? So we have to find the degrees of freedom, and this is the final step, right? And degrees of freedom are simply the number of rows minus 1 times the number of columns minus 1. So for this particular problem, there was 2 rows and 2 columns. This is our original table. So there were 2 rows and there were 2 columns. So it's 2 minus 1, which is 1, times 2 minus 1, which is 1. So that gives us a degrees of freedom of 1. So what we have to do is we have to go to the appendix in the back of our book, and we go to table number 8. And table number 8 reads chi-square distribution, right? So it's pretty simple, right? So the first column reads degrees of freedom. In this particular case, you go down 1 because you got 1 degree of freedom, and you go over on the rows to 0.05 because we're willing to be wrong 0.05% of the time, right? And we get a critical area of 3.841. And our chi-square is 2.0, right? So again, is this chi-square greater than or less than our critical score? And let's call this a critical score, right? In this case, our chi-square is less than our critical score. So this means that we accept the null hypothesis. There is independence here. These things are not reacting with one another, right? They're not related, right?